Good morning, ladies and gentlemen. We're Group 23 and we're here to present our structural design report. The purpose of this report was to design a storage shed to be located at Mudgee Bar on the Gold Coast. It was assumed that a 6 by 10 metre portal frame with the roof pitch less than 5 degrees would be the most suitable solution. To find the most economical design, various calculations were done to find the most suitable members that could be used to construct the shed and be as light as possible. All the calculations performed were completed in accordance with the Australian standard. The proposed location of the site in Mudgee Bar is on level ground surrounded by scattered trees. This classes the site as a terrain category 2. This particular site will have shielding and a topography multiplier of 1. So, how long is that?
Word till it works. Yeah.
Wait, don't worry, I don't know how to start.
I'll just leave that key video.
Yeah, it's good.
Just say I'm going to talk about wind load.
I'm going to talk. Right. I will be talking about the wind, dead, and live loads, and which is why we chose the pylons and rafters that we chose. As our structure is positioned in the region B and with the accordance level of 1, the wind gust return period was found to be 100 years, and thus it was found the regional wind speed was 48 metres per second. Once the wind loads were calculated, the dead and live loads due to the sheeting, pylons and rafters were determined. As our structure was intended to provide adequate strength for provided conditions, whilst also being as economical as possible, due to the dead and live loads found, the roof sheeting used was Integrity 820 0.42, and the custom orb 0.42 was used for the wall sheeting. We chose the lightest universal beam for rafters, being UB 150 UB 14, and the pylons we chose were Z 150 15.
The first attempted rafter was a 150 UB14, which was thought to be capable of varying the imposed loads. However, upon inspection of Table 2 in Study Guide Part 2, it was found that the effective length of the 150 UB14 cannot be more than 5 metres. Hence, fly bracing was necessary to reduce the effective length with a corresponding value of phi and d. Calculations found the maximum moments and shear found in space gaps were less than the calculated allowable, hence the beam chosen was acceptable. The column selection process was similar to the rafter selection, however with the inclusion of axial tension and compression. Results showed that 150 UC 14.8 was more than capable of bearing the imposed loads. Discussion took place on whether to reduce the column member to a hollow section. However, when regarding the complications that arise with hollow section member calculations, it was decided to continue with the universal column 100 UC 14.8 outlet.
For the rafter to column connections, we ended up using a 250 by 90 by 7mm plate connected with 4 M16 bolts. For the welds, we used general purpose full penetration butt welds along the full length of the flange, and general purpose fillet weld along 25mm either side of the web. Both these welds were 4mm in diameter. For the rafter to rafter connection, we ended up using the exact same plate size and same size bolts. This is simply due to ease construction and also mean no mistakes were made. Calculations were all the same. It makes everything much simpler. Although the difference for this connection was mainly the welds. For the flange welds, we ended up using a structural purpose full penetration butt weld along the full length of the flange. But due to the very low shear, we ended up using only 5mm either side of the web as a fillet weld. We could almost ignore the shear, but we decided to make it 5mm as a bare minimum just for safety. For all these connections, we assumed that the angle was completely zero, thereby making the actual calculations much easier.
Once the
final design was settled on, a stability check was conducted. It was found that fly bracing would need to be incorporated into the rafter design due to the 150 UB14 universal beam not being capable of bearing a member with an effective length greater than 5 metres. It was more efficient to add fly bracing than increasing the rafter size. Our calculations proved that one fly bracing would be sufficient for the span of the rafter. The stability check also resulted in the need for cross bracing. Assuming that cross bracing is only a tensile restraint, there was no need to calculate the ability of the member in compression. A 25 by 25 equal angle section with a thickness of 3 mm was found to have the required tensile strength to considerably reduce the deflection. Thank you for your time.